So, good afternoon, everyone. Uh, Today is basically this extra session of this basic linear algebra course. So, today we'll basically recall all of these. We will cover all of the topics that we already covered in previous 8 weeks. So, if you have any specific query or any specific question regarding any of the topic, you can ask, or I just start from the beginning and start with a little one and two example of all the topics. Try to cover. So if you have any, sorry, I hope my voice is audible. So if you have any query regarding the previous topics that till date we have covered, uh, you can ask over here so that I can clear. So this is basically the extra session. Okay. So So none of you have any queries regarding any topic. Okay, so I'll start with the beginning. So at first, basically, we have start with the row echelon form. So this basically helps us to sorry, this basically helps us to find out the solution of any system of equations, right? So we know that how to do this, all these things. Then we have studied the row reduce or reduced row echelon form. That is a much more a reduced form to make if a system to get a very clear vision of the solution of matrix. And then we start talk about the rank, all of these things. So we know that in like I just start with one example of row echelon form. So the first example, I know you all have proper idea about what is a row echelon form, but since this is an extra session, so I'll start with this example. So there's nothing new about this example for you if you have already studied this topic. So I have this A matrix that is a 2, 4, minus 2, 4, 9, minus 3, minus 2, minus 3, 7. And then we have 2, 8 tail. So how does we solve this solution? So we first make an augment. I'm not doing all those things. I just start with the procedure and then you go through all those things. Okay. This so we all know we do this row echelon form, and if we get this 0 equals to 0 format in the last row or the last two row, then we can say the system is solvable. If we get the 0 equals to some non-zero number, then we can say that the system is not solvable. Okay, so we do this. We need to change R to something like, let's say, R1 minus half R2, I guess, and R3 prime is R1 plus R3, and then we get this 0. And this is, I think, better if I do this thing in the solution with. Right. Yes, this is. Let's put that as three. Mhm. Mhm. Times five. And then next you have to make this term 0 because we get this one is a pivot and this one is a pivot. So we know that row reduced form, in row reduced form, we just need to make the element that is below the pivot element. We need to make this one, that term should be 0. So for that case, you do that is R3, you need to change R3, so you get R3 plus R2, and you will get some sort of rows, and from there we get the solution of X, Y, and Z, right? So this is basically the row echelon form. Okay, so and then we move to that thing that is a reduced row echelon form. So reduced row echelon form is basically a little more reduced version, means obviously that is already shown in name. So here in reduced row echelon form, let's say I just called it RRE. So in reduced row echelon form, we have to make all the pivot elements, whatever the pivot elements, we have to, let's say we have 3 cross 3 matrix, let's say 3 cross 4 matrix. Okay, so we have to make all the pivot elements 1, and obviously below the pivot element should be 0, but above the pivot element also we want to make this 0. And let's say I have something, 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 something. So this is basically the reduced row echelon form. Okay. So we have to make all the pivot elements 0, and obviously the below and above the pivot element, all the pivot elements should be 1, and below and above the pivot element should be 0. So obviously you can see from here, if if you have a square matrix, that means if you have a exact number of, if the number of equation and the number of variable is same, if the matrix is square and also the invertible, then we get that the row reduced echelon form is basically identity, right? So from here, let's say if we can see another example, let's check whether this matrix, the row reduced row echelon form, can give this matrix an identity or not. So I have something like this matrix, so I need to make it a reduced row echelon form. So first I need to do, I need to change R2, so it's R2 plus R1. I do not need to do anything about R3, so it's 0, 1, minus 1, 0, minus 1, 2. So now I need to change R3 as well. First I do this row echelon form, okay? So R3 plus R2, 1 minus 1, 0, 0, this, 0, 1. So we get this row echelon form. Now we need to do the reduced row echelon form, right? So we need to change the R1 because we need to change this element. Okay, we need to make this element to 0. We need to make this element to 0 for R2 case. So we need to change R1. So what would be R1? So R1 should be R1 plus, first we need to do the R2 thing. So because we need to make this term first 0, we need to make this term first 0. Okay, it would be easier to understand. R2 plus R3. So what we get, 0, 1, and this one 0, because we changed the R2. Obviously, this thing be 1, and then we change R1, which should be R1 plus R2, and we get 1, 0, 0, 0, 1, 0, 0, 0, 1. So that means this matrix, definitely you have a 3 pivot elements in 3 different rows. So that means this matrix is a invertible matrix. So obviously for a square matrix, if the matrix is invertible, the reduced row echelon form would be an identity. Okay. So next we talk about, so from here we get the concept of rank of a matrix, right? We got the concept of what is the rank of a matrix. Rank of a matrix is basically nothing but the number of independent columns. Number of, how do you find the independent column? the column that exists the pivot element is basically the independent column, right? So here this is the pivot element, this is the pivot element, this is the pivot element. So every column exists a pivot element. So we know that there are three pivot elements. That means the number of independent column is three. So definitely the rank of the matrix is three, right? So from here we get the concept of rank of a matrix. Now we get to know about the how to find out the solution. We get first we got the concept. We know we understand the concept of null space and column space, right? So what is basically the null space? So null space is basically the solution. Let's say null space. So what is null space? Is basically solution of Ax equals to 0, right? So we need to find out all those x who gives this Ax equals to 0, who basically satisfy this Ax equals to 0 equation, this equation, right? So those x basically the null space of A. Okay. So what would be the what would be the dimension of null space? So we know that if let's say we have something like, I'm not writing anything, just to show. Let's say I have 3 cross, just to make 3 cross 4 matrix. Okay. And I have something like x1, x2, and x3. Sorry. And x1. So this is 0, 0, 0. So what would be the dimension of null space? So this is basically 3 cross 4 matrix, right? So A belongs to, let's say talk about real number, it's a 3 cross 4, right? Or rather say n cross n cross n. So what is the dimension of null space? So dimension of null space would be the number of the columns. So dimension of null space of A should be m, right? Because there in null space there would be every vector consists of 4 elements, right? So dimension of the null space would be 4. So in particular this example, that it would be m. Similarly, what is the column space? Column space basically, it is basically we need to find, it is basically the space that is spanned by the column of matrix. Okay. So here, so the column space of A is basically a space that is spanned by the column of matrix A, right? So when we can say that Ax equals to B is, so from here we get the question. The question is when we can say that Ax equals to B is solvable. So the question is when we can say that this Ax equals to B is solvable. So do you have any answer for that? I mean, let's forget about that row echelon form and all those things. I'm not
If
talking
A
about row.
is linearly independent.
Not like that. A is linearly independent. Here, I'm just talking about the column space. So if we can say, so obviously you can see first of all what would be the dimension of the column space. The dimension of the column space would be Rn, right? Because the dimension of the, what will be the dimension of the column space? Just a minute. Just find out one question for that. So here for n cross m matrix, that means where the number of rows equals to n and number of columns equals to n. So what is the dimension of the null space means the number of the columns, right? Because there are four elements in every vector consists of four elements. But here the column space is basically every consists of three elements because we need Ax equals to b to be solvable. That means that b vector should lie in the column space of A, because you can see that every column here, you can see that every column consists of three elements, right? Every column consists of three. For this particular example, you can see that every column consists of three elements. It's not four elements. Number of column is four. So here every row consists of four elements, but every column consists of here three elements. So that means the column space. So obviously, if anything spanned by the column of this A matrix, that means all the vectors consist in the column space must be all the vector consist with three elements, right? Because they are spanned by this column. I think it is understand to all of you. So that means if this b vector, so here b vector is basically 0, but normal this is basically the homogeneous case. For the non-homogeneous case where the b vector is not a zero vector, it's basically something else. So if b lies in the column space, means if we if uh, we can create b vector by some linear combination of a vector, a linear combination of columns of A. If this happens, that means that B is solvable. Okay. So if B does not lie in the column space of A, that means we do not get the exact solution. That means there does not exist any solution. And for that case, what should we do? We do some least square error. We need to do some least square error. That means we need to do some sort of projection. We have studied about the projection. We have studied about the projection on a line. But here I will talk about the projection on a space. Okay, just to clear this thing. So if P lies in the column space of A, then Ax equals to B is solvable. Right. So dimension of what will be the dimension of column space? Dimension of column space of A is basically n for particular n cross m matrix. Okay, because every column consists of n number of elements. Okay, so you need to think of like you need to think of something like that. There is a picture something. I Let me just draw a picture for you. Then it will be clear. So we know there are four fundamental space. So basically there are four fundamental spaces. What are those? The first one is, let's say, null space. Second one is column space. Third one is row space. And fourth one is left null space or null space of A transpose. Okay, null space of A transpose. So So the picture is something like that. You can see over here that null space that belongs to, if let's say this all corresponds to particular a matrix, right? Let's say I'm saying that matrix is A, and that and A belongs to some real number n cross A. Okay. So null space, definitely we have studied that the dimension of null space is M. Okay, that means null space belongs to Rn. So column space belongs to, we have studied over here that every column consists of n number of elements. So column space belongs to Rn. Okay, for n cross m, where number of rows is n, number of column is m. So what will be the row space? So row space is basically the column space of A transpose. It's nothing but a column space of A transpose. So column space of A is obviously n number of elements. So column space of A transpose should be m number of elements, right? So it is dimension of Rm, and this belongs to dimension of Rn, right? So you can see row space and null space both are perpendicular to each other in the same dimension. So if this is a row space, if this something a row space, okay, I think I should write something like that. If that angle, I don't know, I mean whether it looks like a perpendicular or not, but that angle is perpendicular. If it's a, let's say, row space of A, and this is a null space of A. So this whole thing, this is basically Rm. So inside this Rm, let's say this portion is the row space. So inside this Rm, this portion is the row space and this portion is the column space. So every row space is perpendicular to the null space. Okay. Now if we see Rn dimension, so in Rn dimension, column space and left null space is there. So if this is the Rn space, okay, so here you can see if this one is a column space of A, so this should be the left null space of A, or called null space of A transpose. So this is, let's say, column space of A, CA. So this is called row space, and this is called null space of A transpose, or call it a left null space of A. So these two are perpendicular to each other. Okay. So this is Rn dimension. So I hope that picture is basically clear to you. So row space is perpendicular with a null space, and the column space perpendicular with a left null space. So definitely, every if B lies in the column space of A, then we can say the system is solvable. Now, if it is not possible, it is not always the case. Like, obviously, if we do the row echelon form, we get something like 0 equals to some non-zero number. So that means we conclude from here that the system equation is not solvable. So for that case, what should we do? So for that case, we do a projection, or we do the least square. We need to find out the least square solution, where obviously we do not get the exact solution, but the actual and the least square, the error between the actual and least square solution is basically very small. We need to basically minimize. So what is basically the least square? error, we need to basically minimize. We need to basically minimize this ax equals x minus b. Minimize this error. That two norm error. We need to minimize this error. So obviously x equals to b is there. So that means x minus b equals to 0 over here. So we can write it this equation. So if b lies in the null space A, in the column space of A, so this is basically we get a particular solution. We get a solution for x, and obviously this equation satisfied for that x. But if we do not get that particular x, we need an x which basically try to minimize this error. I mean, obviously we do not get the exact 0, but we get a solution which gives us very near to 0. We get the value of x. For that case, this x minus b will give a will give a solution, will give a value which is very near to 0. So we need to minimize this least square solution. So this is basically related to the projection on a space. So we have studied that projection on a plane, right? A projection on a line. So we have studied previously projection on line. So what was the projection on line thing? So we have something like this. So this is something like A, line A, and we need to project B over here. So that means we basically draw a perpendicular and we need to find minimize this error, this E, right? And this is basically the P. So when we project B on A, we get this vector small p, right? So what was the actually formula for that? The formula was the small p is basically A into x, right? So definitely A into A transpose B divided by A transpose A. So that means this was our projection matrix, right? If you go through that previous discussion, we have already studied that this is the projection on a line, definitely. So here we can, you can, I'm just asking you one question over here. So the P matrix, this is basically the projection matrix, which is basically A. So A is something like A1, A2, A3. Uh, let's say up to some A. We don't know how many elements over there. So let's say Rn dimension. So A is something like that. And we have A transpose divided by A transpose A. So the denominator A transpose A is basically a scalar, right? So this is basically a matrix. This the numerator A transpose is basically the matrix. So for that case, the question to you is what is the rank of projection matrix P for this particular case? For this particular case, what would be the when we project any vector onto a line? So what is the rank of this projection matrix P? What would be what is the answer? You please get to join over here to give some answer. So you do not need to worry about the part of the denominator. It's something. It's basically, let's say, consider that this is basically divided by some scalar number. So you need to worry about. You need to think about this, the numerator part. Denominator is okay. I mean, it doesn't give any contribution to the matrix. It's just basically divide the matrix If it's a integer, it basically divide the matrix and divide the every element. If it's a fraction number or it's a less than one, you basically multiply. So you do not need to worry about the numerator. It's just sorry, denominator. You just think about the numerator. What would be the rank of this projection matrix? Anyone? So A is basically a column, right? Let's say don't consider up to n. Let's say A consists of three element A1 and A1, A2, A3. It belongs to R3. Okay. So one thing for sure that matrix, whatever matrix that we got, whatever the P matrix that we got, that is for sure is a square matrix. It won't be an rectangular matrix, right? So that it belongs to R3. So what would be the A transpose? So A transpose is something like A1, A2, and A3, right? So when you multiply A into A transpose, so what will you get? This is A1, A2, A3, and then A1, A2, A3. So what we get? A1 square, A1, A2, A1, A3, A1, A2, A2 square, A2, A3, right? And this is A1, A3, A2, A3, A3 square. Yeah. So you get a matrix something like this, right? So you can see that the rank of this matrix is basically always be a 1, right? It will always be a 1 matrix. The rank of this matrix is always be a 1. Let me show by an example. So let's say 1, 2, 2. So if we multiply with these things, what will you get? 1, 2, 2, and then second 2, 4, 4, third 2, 4, 4. So you can always, if you do the row echelon form, you can always make the other two rows 0. Because ultimately, the row 1, is row 2 and row 3 are basically the multiplication. They are basically related with some sort of multiplication factor. So instead of 2, if you put over here 3, let's say, or any number. So what do you get? You get 3, 6, 9, right? So every time you can basically eliminate the other two rows. So we will definitely get a rank 1 matrix for that case. And is it clear to everyone how this rank of this matrix is always 1?
Yes, sir.
Yeah. So for that case, so definitely A transpose. So if we have if we multiply a vector with its transpose, if multiply a column vector with its transpose, so always every cases we get a rank 1 matrix. So the projection matrix for this case, whenever we project any vector onto a line, so we will get a projection matrix which is rank 1. Now we move to the projection on subspace. So when we talk about projection on subspace, so here no longer a vector, it's basically a combination of vectors over there. So that means we get a matrix. We will not definitely get a like A is here only a vector. So now it is not a single vector. It is basically the combination of vectors. So definitely instead of small a, which denotes a vector, it will be a matrix. It will be a capital A, that basically the matrix. So the picture is something like that. So this is a space, something like subspace. And the question is, you need to, so I have a vector something like that. So this is like B vector, okay, which is outside this space, and I need to plot it on that. I need to plot it on that space. So this is basically, let's say, this is my error, and this is basically the small p vector. So for that case, let's say this is a space spanned by vectors a1, a2 to an, and this space where ai belongs to Rn, or all I equals to, or I equals to 1 to n. Okay, so that means all ai, so a1 consists of m number of elements, and there are n number of uh, a's are there, ais are there, n number of ais are there. So here we assume that these a vectors are linearly independent. So we need to find out the small p. Okay. So what would be the small p? So obviously small p, this is basically the small p that I'm talking about, and this lies on this space. Okay, some space. Let's say call this space as a, let's say, okay, v. V is this space. Okay, so any vector lies on this space, and here we have said that sorry, all the a's are linearly independent. That means we can we can define a vector, we can design this p by using these a's, right? All this linear combination. So let's say I'm talking about, let's say, x1 a1 plus x2 a2 up to, let's say, xn an. So these are the multiplication fact, scalar multiplication. So we can write it like that. So if p, so don't forget this a1 is something look like this, a11, a12 up to a1n, right? It's better like choose I over here. AI1, AI2, AI. So all the AI are some look like something like that. Okay. So if we write it in a matrix vector format, that means, and let's say x hat is equals consist of x1 hat, x2 hat up to xn hat. Okay. So it would be something like that, right? A11, A12 up to A1m, A21, A22 up to A2m, and then AN1, AN2, ANM. And this is x1 hat, x2 hat up to xn hat, right? We can write this equation in the following format, right? Up to this, it is okay for everyone. So that means we call this, this is call this matrix A. This is matrix A, and call this is vector A, right? So we don't know anything about this x, right? We need to find out that. What would be that multiplication factor? We have A's, AI's. So we need to find out this one. Okay. So obviously, so here we have a vector B, and we know that this error is perpendicular with T, right? So what is the error? Error vector error vector E is equal to B minus B, right? So something B minus A x hat. So now we know that this E perpendicular with all the AIs, right? Because there are lots of AIs are there, and this E vector is perpendicular with every AIs. Okay, it's not, it is basically when we say that any vector is perpendicular to a space, that means that vector is perpendicular to the every vector which lies in this space. So Z is perpendicular to XY plane. So that means Z is perpendicular to, in XY plane, there are many vectors are there. So every vector is basically perpendicular with every vector on the XY plane is basically orthogonal to the Z vector. So this is similarly something like that. So E vector is perpendicular to the space V. So that means every vector that lies on the space V is basically orthogonal to the vector E. So that means E is basically perpendicular with every AIs. So that means when that means what does this implies? This implies that A1 transpose E equals to 0, right? A2 transpose E equals to 0 up to AN transpose E equals to 0, right? So how can we write these things? So A1 transpose, what is E? E is B minus AX hat. This is equals to 0. A2 transpose B minus AX hat. This is equals to 0. Now AN transpose B minus AX hat. This is equals to 0. Right? Now this is again matrix. This is again, we can write this system of equations into a matrix vector format, because this is vector, and we can write it matrix vector format. How? We can write it something like that. A1 transpose, which is basically a row vector, A2 transpose, which is basically a row vector, up to AN transpose, which is basically a row vector, multiplied with only single vector, which is B minus AX hat, which gives a 0 vector, right? So definitely, if these things, is called A, so definitely this thing is called A transpose B minus AX hat equals to 0. Now we multiply A transpose B minus A transpose A x hat equals to 0. So here what we get, A transpose A x hat equals to A transpose B. So x hat equals to, multiplying both sides with the A transpose A inverse. So why this inverse exists? Because previously we have already said that the column of A are linearly independent, because we have already mentioned that A's are linearly independent. If A's are linearly independent, so definitely A transpose A, which is a square matrix, we get an inverse. Okay, so we get the value of x hat. Now we need to find out the p vector which is projected on the plane, which is A multiplied with A transpose A inverse A transpose B. So these things is basically a projection matrix capital P. So this is basically something like that. Now it may looks like these things here. Up to that point is clear to everyone, right? So
Yes, sir.
yeah. So P matrix is something like this, right? Now it may look deceptive because we know that A, now A B inverse is equal to B inverse A inverse, right? Something like that. So from using this property, we get A inverse. This is A transpose inverse A A transpose, right? And then what we get is I. So that means P is equal to I. Is it true? No, it is not true, because we can't do this kind of thing. Here A transpose A inverse, we cannot write something like A inverse A transpose inverse. We cannot write it something like that. Why? Because here A matrix is a rectangular matrix. If you see from the equation, we have said that it is spanned by vectors. How many vectors? N number of vectors, A1 to AN, and all the AIs belong to Rm, right? All the vectors belongs to Rm. That means the element consists of each AI vector is m number of elements. So definitely that A matrix never be a square matrix. But if Rm, that m equals to m, if m equals to m, if in that situation, if m equals to n, let's say the number of elements, number of vectors, that is A1 to AN, and all AIs belongs to Rn itself. That means the each AI consists of n number of elements and n number of vectors are there. Then we can write it something like that. Then our P matrix is now, it will definitely then is an identity matrix. Since here A matrix is a rectangular matrix, so obviously we can't do the inverse of any rectangular matrix, because we can't do any determinant of any rectangular matrix. So we can't write something like that. So this may look some deceptive, but we can't split these things. So you need to remember that. Okay. So we can't do this kind of thing. So now do one example from here. So obviously, can you tell me, here I have said, that there are m number of elements. Sorry, there are n number of elements, n number of vectors, and each vector consists of m number of elements. Obviously, m and n both are, and also defined number. And also, I have said that all the AIs are linearly independent. So, can you say what would be the relation between n and m? What would be the relation between n and m? So here I have said there are a1 to an number of vectors, and each AIs belong to Rm. So what would be the relation between n and m? Like greater than, less than, equal to. I'm talking about this relation. So here, yeah,
M
yes,
is less than or equal to n.
no, you said it wrong. N is less than m, not m is less than n. AI consists of, let's forget about m. I'm just, let's say q. Okay, it would be mn is very phonetic. So AI, let's say, belongs to RQ, and there are n number of AIs. That is, there exists A1, A2, up to AN, right? And the next thing that I have said, right, is all the vectors, A vectors, are linearly independent. Okay. So here basically n is less than q, guys. AI. Why n is less than q? Because if n is greater than q, so I have, let's say, a1 is something like 1, 0. Okay. A2 is something like 0, 1. Okay. And let's say I have a vector a3, which is something like anything, -1, 1. Is it possible that this three vector is linearly independent?
No, sir.
Never be possible, right? So that means here n, here in this example, n is 3 and q is 2. So if n greater than q is, this implies is are not linearly independent. If n less than or equals to q, this implies is are linearly independent. Here A1, A2 are linearly independent. A1, A3 are linearly independent. A2, A3 are linearly independent. But A1, A2, A3 are not linearly independent. So that means it always has to be n should be less than or equal to q. So definitely the matrix that we get is mostly either a square matrix or a tall matrix. We'll never get a fat matrix, because if we stack all the AIs over there, because my Q is greater than M, my number of rows would be greater than number of columns. So either we will get greater than or equals to. So either we will get square matrix or we will get a tall matrix. We will never get a fat matrix where the number of rows is less than number of columns, right? So you just need to think of that. So the example is something like that. So if straightforward, basically, if A is equals to 1 0 1 1 and 1 2, and B is something like 6 0 0, find exact small p and capital P. Okay. So we have something like A is something like tall matrix. So what is the formula? So my formula is something like P equals to A into A transpose A inverse A transpose B. So where capital P is basically A into A transpose A inverse A transpose, and X hat is basically A transpose A inverse A transpose B, right? So we need to find these two. I mean, anything we can find it from here. So A transpose A. What will be the A transpose? 1 0 1 1 1 2, and this is 1 0 1 1 1 2. So this is 3, this is 3. So definitely this is 3 and this is 5. Since these two columns are linearly independent, so definitely A transpose A will be invertible, right? So what will be the A transpose A? Inverse will be 1 by A transpose A into adjoint of A transpose A, right? Something like that. So it's a 1 by 15 minus 9 is 6, and this would be something like, I think these two changes and the negative sign would be there. So A transpose A inverse would be something like half, half, half. We can check that whether this is A transpose A inverse or not. I think I have done correctly. So, I mean, for 2 cross 2 matrix, it is very easy to find out the A inverse without finding out the, I mean, this is a short process. If for 2 cross 2, the adjoint of A is basically you can interchange this, this diagonal element position, and you do not need to interchange the diagonal element position. They will be the same. Just you put minus before that term, before that basically that element. If it is a minus 3, then it will become a plus 3, something like that. So this is basically, it is basically easy to find the adjoint for 2 cross 2 matrix, but it is not that much easy for 3 cross 3 or 10 cross 10 matrix. So what is my capital P is A into A transpose A inverse A transpose. So something A is 1 0 1 1 1 2. think 1/6 is over there. 5 minus 3 minus 3, 3. And this is inverse, and this is 1, 0, 1, 1, 1, 2. So you can do that multiplication. You will get the matrix P, small p, or x hat is something like A transpose A inverse A transpose B, which will be 1/6. 5 minus 3 minus 3. It's 1, 0, 1, 1, 1, 2, and then B 6, 0, 0. Okay, and this is small p, which is basically capital P into B. We will get the answer. Okay, so this is basically projection on a subspace. Uh, So this projection on a subspace is basically very similar to the least square approximation. Uh, so as I have said that when Ax equals to B has solution, this has solution when B lies in the column space of A. But what if B does not lie in the column space of A? So in the previous example, what was our A? So A was 1, 0, 1, 1, 1, 2, and what was B is 6, 0, 0, right? So if we do the row elimination, R2 is basically R2 minus R1, R3 is basically R3 minus R1. So what we'll get? 1, 0, 6, 0, 1, and this is minus 6, and this is 0, 2, minus 6. Okay. Now I need to change R3. So R3 is basically R3 minus 2 R2. So what we'll get? 1, 0, 6, 0, 1, minus 6, and here 0. This is 0, and this is definitely not 0. So what would be this? So this is basically the augment. So this is 2, this is 12, 6, minus 6 plus 12, this is it, plus 6. So from here you can see that this is not a 0 equals to 0 format. So that means this is basically the augmented version. So this is not basically a 0 equals to 0 format. That means system has no solution, right? So for that case, in that scenario, we need to do least square approximation. That means we need to find out a solution which is very nearer to the exact solution, but not exact one. So that means this is x hat equals to b for that case. So x hat is basically the approximated solution. And what we do, we multiply both sides with A transpose. We get this kind of thing. And since A transpose A has a linearly independent columns over here, so we can do this kind of thing. X hat equals to A transpose A inverse A transpose B. So it is pretty much that projection, right? What we have studied over here. Sorry. This kind of thing, right? It pretty much looks like this. So this is basically the least square approximate least square solution. So this is all about the projection. And then we studied about the Gram-Schmidt method, where we basically uh, design an orthonormal vector. If two or more than two vectors are linearly independent, we can make them orthogonal to each other, and by dividing its norm, we can do this the orthonormality. So Gram-Schmidt is the one thing by which we can do the orthonormal solution. And so we have also studied the determinant. So the determinant is basically like the properties of determinant is something like that. Sorry. So we know that we have studied this, right? A square, AB, AC, BA minus B square, BC, and CA, CB minus C square. And we need to prove this equals to that. So in case of we have studied that in case of determinant, we can take a element common from particular row or particular column, which is not possible the case for matrix, because when we multiply any, here we have seen that when we multiplied by any constant, matrix multiplied by any constant, so each element is basically multiplied with that. But in case of determinant, the property is a little bit different. If we multiply particular row by element, so we can multiply that. So obviously we can take common from row 1, row 2. We can take common A from row 1, B from row 2, C from row 3, and we will get A, B, sorry, minus A, B, C. This is A minus B, C, and this is A, C, sorry, A, B minus C. So here first I take common A from row 1, B from row 2, and C from row 3. Now if I take common A from column 1, B from column 2, C from column 3, so we'll get A square, B square, C square, something like minus 1, 1, 1, 1 minus 1, 1, and 1, 1 minus 1. Now do the column operation or row operation, you will get this 4 square, B square, C square. I think rest you can do that. Okay. So this is something like determinant. So we have studied about the diagonalization. So if a matrix, we have studied that if a matrix have a independent eigenvalue, then definitely the corresponding eigenvector will be independent. And for that case, that matrix can be, we can diagonalize that matrix, because we have in diagonalization we have studied that in between you have any queries regarding any topic, whatever we have covered till date, you can ask me. So diagonalization is, let's say lambda is equals to, let me just recall that formula. Yeah. A sin inverse A is, and A is equals to S lambda is inverse. So S is basically, you can call it an eigenvector matrix over here. So if lambda, I mean, if the eigenvalues are different of A, then obviously for different eigenvalue, we get a different eigenvector, and those are linearly independent. So definitely S is basically a full rank matrix. S would be a full rank matrix, so we can find out the inverse of that matrix. And if, let's say, if there are similar number of eigenvalues of A has similar number of eigenvalues, then we have to check whether the algebraic multiplicity is equals to the geometric multiplicity for that particular eigenvalue is not. If it is not, then definitely we cannot find out the diagonalization. We cannot diagonalize that particular matrix A. For that case, I have shown to you how to find out the generalized eigenvector, and that generalized eigenvector need to use to find out to create that S matrix, and then we do the inverse process. But for that case, we do not get the exact diagonal. We do not get the exact diagonal value, exact diagonalization. That would be a similar matrix whose property would be similar, but that is not exact. So I think that topic was clear to everyone when I have discussed with you. So I'm not going to discuss this topic again over here. So last, and then we have, okay, let's do one thing. Okay, so here I'm just doing one thing. Usually we can do this mistake. So let eigenvalue of A is lambda and eigenvalue of matrix B is, let's say, beta. Okay. So what would be the eigenvalue of matrix A multiplied with B, AB? Okay. So we know that we can do this kind of thing, ABX, right? Now we can write, I used black. So AB is a matrix multiplied with a vector. So definitely eigenvalues, it would be something like some eigenvalues, let's some eigenvalues gamma into X, right? So here the proof is something which is looks like deceptive, okay, which is true, but that is basically deceptive. It is false proof. So where we can do the mistakes. So this kind of thing. So where X is an eigenvector and this is eigenvalue, right? So so you may think of like something like that. So this is basically the actual thing. So you may think, okay, I can do this kind of thing. So B, so definitely what logic said, Bx equals to some beta into X. This is basically the eigenvalue eigenvector structure. So we can do A into beta X. So beta is a scalar. So we can shift it over here and then do the AX. So what would be the AX? So AX equals to some lambda into X. So what would be this? Beta lambda X. This looks like very easy. Okay, that means the eigenvalues of AB is multiplication of that eigenvalues of A and eigenvalues of B. But this whole proof is wrong. This whole proof is wrong. Why it is wrong? Okay, I have said that A has eigenvalue lambda and B has eigenvalue beta, but I have not said anything that they share the same eigenvector. It's not possible. I have not said anything that they are similar matrix. Definitely, they are not similar matrix. If they are similar matrix, their eigenvalue would be the similar, but that's not the case. So here we have already think that B, if X is the eigenvector of B, we have already think that X is also an eigenvector of A, because this is only possible if X is an eigenvector of A, then we can write that lambda into X. This is only possible if X is an eigenvector of B, then we can only write that beta into X, this format, right? But here I have not said anything about that A and B matrix share the same eigenvector. So we can't do this kind of thing. This is completely wrong proof. Okay. So we cannot find out, I mean, from here we cannot find out the eigenvalue of AB, something like that. We need A matrix, we need B matrix, we need to calculate the eigenvalues accordingly. We can't do this kind of thing. From the eigenvalue of A and B separately, we cannot find out the eigenvalue of AB. So this whole proof is a wrong proof. Okay, is it understand to all of you? Okay, so we have studied about some linear transformation. I think there is nothing to worry about linear transformation. We have studied about in abstract algebra, we have studied about something like polynomial space, right? So in that case, you have not, I'm not going through all those things. I just, you may have checked the video, since only one person present at that time. So is a, since till date we have talked about only a vector space, which deals with only the numbers. So here in abstract vector space, specifically here we have discussed about here I have discussed about the polynomial vector space, where we are basically dealing with polynomials. Okay, it's not no longer a number, it's basically a polynomial. So more or less they have the same property. Okay, so obviously if we talk about a vector space, so we need to mention what operations are there. Addition and scalar multiplication, vector addition, scalar multiplication. So these are two the operation over there, and all the rules are basically the same. There is nothing new about the rule. The rule that is applied for a normal vector space, similar rules can be applied for the polynomial vector space. So a polynomial vector space is basically the set of polynomials. Obviously, if you add two polynomials, that definitely lies in that particular. If you add two polynomials, then you can that resultant polynomial lies in the particular space. If you multiply polynomial by a scalar, definitely we will get a new polynomial which definitely lie in the particular space. So there one thing that one small thing that I haven't discussed previous class, that was a finite vector space. Obviously, what is finite vector space? Finite vector space means when the dimension of the vector space is finite to us. Like how we can find the dimension, how we can say what is the dimension of the vector space, how the dimension of the vector space related to the basis of the vector space. We have already studied that the number of vectors that exist in that basis space is basically the defines the dimension of that vector space. Okay, so we have already studied that. So in case of finite vector space, so obviously the number of vectors in the basis should be finite. That means any vector that can be finitely determined by this basis are basically the finite vector space. If the vector space is said that it is infinite, that means there are lots of vectors exist in the basis vector space, and we do not know how many vectors are there. The number of vectors in the basis space is infinite. So definitely none of the vectors in that infinite dimension of vector space can be represented by a finite number of element, because the number of bases are infinite. So obviously we do not know how many bases are there, so we can't express any vectors of that infinite vector. So definitely we are basically up to that point, we are basically dealing with finite number of vector spaces. The polynomial space is basically a vector space, and why it is basically vector space? Because it satisfies all those rules, all those 8 axioms. They basically satisfy all those axioms. So as we have already studied that for a particular vector basis is not an unique one. Yeah, definitely every space has a standard basis, but we can choose any vectors, any set of vectors as a basis, just to just two things you need to keep in mind to make a basis. The first thing, all the vectors should be linearly independent, and definitely the number of vectors should be exact one, right? That means in case of 3 dimension, this is basically the standard basis. So here all the vectors are linearly independent, and since the dimension is 3, so definitely there has to be a 3 number of vectors in the basis space. So similarly for polynomial P2, that means P2 means the degree of the polynomial in that space should be maximum could be 2. That means the polynomial maximum polynomial that can exist would be x square or 1 plus x square, this kind of thing. So this is the standard basis. So degree of this polynomial, this P2 space is 2, but the dimension is 3. Definitely, you can see there are 3 number of elements. Similarly, for Pn, there are n plus 1 number of elements, but dimension degree is n. So here are some questions related to some polynomial space that you can check. I'm not go through this. If you have any kind of problem, you can ask me right now. Otherwise, there is nothing to talk about because already I have talked it in a lecture video 8. So this is just an extra session. So just to you have any particular doubt, you can ask me so that I can clear that doubt. So this all about the polynomial space. There are a few examples that I have mentioned over here. And then it comes like inner product space. So what was the inner product space? It could be, I mean, every space could be a real space, or could be a complex space. So till now we have talked about only real space because it is basically easy to multiplication and addition kind of thing in a real space, right? So these are the 3 axioms that need to be followed. If these 3 axioms can follow, then this is called an inner product space. This is also a vector space because this inner product space, the elements inside this inner product space also follows these rules of the vector space. But in particular, this inner product space, it has some extra axioms that needs to be followed. So this is the particular symbol that basically used to define an inner product. This is basically something like dot product, nothing but nothing more than that. So this is called bracket. Okay, bracket. So this symbol is called bracket symbol. So these are the 3 axioms that need to be followed to space become an inner product space. Okay, and they also satisfy the vector space rule. And here I have already mentioned that obviously when we have talked we have when we were dealing with the orthogonal matrix or orthonormal matrix, because in one discussion we are basically dealing with the orthogonal matrix, and we show that orthogonality is so much important because if the matrix is orthonormal, so we do not need to find out the inverse. Something we just need to transpose, because obviously inverse to find out the inverse is basically a time consuming. I mean, for human and for other software as well. So it is we need to find out we need to come up with a solution so that our computation time should be minimized. So that's why this orthonormality or orthogonality concept comes into the picture. Okay. So obviously here we do not need to find out any inverse. We just need to transpose for orthonormal matrix. We just need to transpose that matrix and we get the inverse. So that's why orthonormality is important. And also the orthonormality of a matrix defines that, I mean, if a matrix is orthonormal, you can say that obviously that matrix could be invertible. I mean, any square matrix is not invertible, but any orthonormal matrix, definitely those are square, any orthonormal matrix are invertible. So here is basically the proof why this orthogonal matrix is invertible. So here we have said that, okay, the question says that S is consist of V1 to Vk number of vectors, which lies in the columns of the matrix, is basically V1 to Vk are orthogonal to each other. Okay, and none of the Vi's or none of the Vj's over here are zero vectors. So none of the Vi's are the zero vector. So here we have to show that S is linearly independent. Okay. So definitely, if Vi to Vk are linearly independent, are orthogonal. Sorry, if they are the orthogonal to each other, so we need to find that alpha one V1 plus alpha two V2 up to alpha k Vk equals to 0. If you remember the linear independency, the definition of linear independency. So if this could be possible only if and only if all the ai is equals to 0, then from v1 to vk all are linearly independent. If any of the ais over here is non-zero term, so that means they are not linearly independent. Okay, so we need to show over here that whatever the ais would be, that is that has to be 0. All the ais has to be 0. None of the ais is positive number, or we can't get any of the ais is positive, any number, not any number, but I mean, if any of the AI is any non-zero number, then definitely this solution says that, okay, that set of vectors is not linearly independent. So if only linearly independent says that all the AI should be 0. So we take the inner product both sides with the V1. We do this kind of thing by using the property of the inner product space. We do the solution, and we, since obviously vi, what orthogonality says, orthogonality says vi transpose vj equal to 0 if I not equals to j, and they are equals to some value, because here we talk about orthogonal, not orthonormal. If it is orthonormal, then obviously vi transpose vi will be 1. If it is orthogonal, we get some value, some non-zero value. So obviously this term would be 0, vi transpose vj, this term would be 0. So only this term will exist. And since none of the vi's are 0, so obviously this is something positive number. This is some kind of number over there. Okay. And this equals to 0 implies that alpha 1 should be 0. Now you can do the similar experiment. You can do the inner product with V2, then VK, V3, then up till VK, and you say that alpha 1, alpha 2, or up to alpha k all are 0, which signifies that all the alpha i's are 0, means or V1, V2 up to Vk all are the linearly independent vectors. So the orthogonality is so much important in linear algebra. It basically makes our computation much easier. That's why the Gram-Schmidt process is so much important. We just try to make linearly independent vector into orthogonal to each other so that it is easier for us to find out the inverse and other computations. So this is all about today's discussion. We basically here discuss the previous, whatever we have studied till 8 weeks. We have discussed over here in a short format, definitely. And if you guys have any queries from week one topic week one to topic of week 8, you can ask over there. Over here, I can answer it. And if you have no questions, then I just stop this recording. This is all about basic linear algebra. Okay. So Shabik, Diptiranjan, Okeshwar, you have any kind of questions regarding the topic, regarding this basic linear algebra?
So
No, sir.
if
So,
we have a 3 cross 3 matrix,
If I
finding
if we have a three,
characteristic value, eigenvalue,
so if we have a 3 cross 3 matrix, and what was the question?
find the eigenvalue,
Uh,
3 eigenvalues.
uh, so
If we
how to find?
convert the
Sorry. Okay, okay. Just complete your question. Okay.
if we convert the matrix into diagonal matrix,
Ah,
then we find the eigenvalue. Will same? Will the eigenvalues be same or different, sir?
no. Obviously, the eigenvalue will be the same because the diagonalization process says that this diagonal, obviously, the here the big lambda and a, the properties of big lambda and a are same. So the thing is, if A is a 3 cross 3 or 4 cross 4, or let's say A is n cross n matrix. Okay. Now it we can diagonalize this matrix. How we can say? So obviously this lambda consists of all the lambda only consists of diagonal elements. Others non-diagonal elements, off diagonal elements are zero, right? So in the diagonal there exist only the eigenvalues of A. Okay. So if A has distinct eigenvalues, so if A is n cross n matrix, so if A is n cross n matrix and n eigenvalues are distinct, none of it is repetitive, n eigenvalues are distinct. So definitely for sure we can diagonalize that matrix because for distinct eigenvalue we get distinct eigenvector which are linearly independent with the others eigenvectors. So definitely the matrix that we design by putting all the eigenvector into the column of S, we get a matrix which would be a full rank matrix. We can find out the inverse. Now the question arises, if the repetitive eigenvalue, what if the eigenvalues are repetitive? So in that case, we have to find out we have to check the geometric multiplicity and algebraic multiplicity of that particular eigenvalue is same or not. If the geometric multiplicity is less than algebraic multiplicity, then it is not possible to find out the diagonal. It is not possible to diagonalize the particular matrix. So that does that means that we can never be diagonalized that? No, it is not. We need to find out the generalized eigenvector that we have already shown, that I have already shown to you. So that thing, so the thing
अब्बा जा
is,
रहा था क्या बोले फोन आ गया
you just mute that Shabik. You can mute yourself. Actually, there is a noise. Yeah. So the thing is, if we can diagonalize any particular matrix, so definitely all the eigenvalues for the will definitely we can see that all the eigenvalues will lie in the diagonal of that diagonal matrix. If it is not possible, in that case we can find out the similarity matrix. We can find out a similar matrix, but that is not exact diagonal. So obviously, although you can see that in similar matrix the diagonal elements consist of the eigenvalues, but all the off diagonal elements are not zero. Here you can see a 1 over there for that case. So this is basically the case for similar matrix and the diagonal matrix. I mean, is it clear to you, or you have asked something different question, or I answer some differently? What is?
okay sir, it's clear sir.
Okay. So here I just stop this recording. So this is all about. If anything, any queries regarding this topic, you can either check the video, or if you have any problem, you can ask it on a forum. Okay. No. Okay. Bye then.
Thank you, sir.
Thank you, sir.
Thank you.